A pump work is calculated to be 1.02 kilojoules per kilogram in the design of a new power plant, a vapor power cycle that we're talking now. A coworker says this needs to be reduced to improve the cycle efficiency. You respond with the recommendation of what? What do you recommend? Increase the condenser pressure, decrease condenser pressure, increase boiler pressure, decrease boiler pressure, none of the above. Okay, let's do this. What's the equation for the thermal efficiency of the vapor power cycle? Would it be something like this where you're getting, hey, the work out of the turbine minus, I know I'm going to consider it a positive work back to drive the pump. And isn't that positive work back to drive the pump given to be about 1.02 kilojoules per kilogram? And then you're going to divide it by Q net, or basically, what's not Q net, the boiler. What comes into the boiler, all that heat added into the working fluid. And from your experience solving a lot of problems, and you'll be shocked every now and then, sometimes you'll see it. Somebody says, I want a quick answer. I'm going to neglect. Engineers love to do that. What do you mean by that? They're like, yeah, I know that if I ate a piece of toast for breakfast, that it changed my body mass. But I'm not worrying about that right now. I'm just going to tell you this is my weight. You know what I mean? It's like, no, what's your weight? Well, it depends if I ate a piece of orange this morning or if I went to the bathroom in the last 2 hours. It's like neglect. Does that make sense? What was the BWR for a decent vapor power cycle? 1%. 1%. Backwork ratio, about 1% or less even. This is a vapor power. This is a pump. Pumps are very efficient. And so what was the backwork ratio? The work, drive the pump, divided by what came out of the turbine. Have you ever been in a science team and the teams are arguing on something completely negligible? You'll get to it at some stage of life where people will be arguing about something completely negligible. Anyway, I have to grade this and move on. It only gets better. Let's continue. Rankine vapor power cycles used to burn coal to generate electricity. A coworker asks you to make a recommendation to improve the cycle thermal efficiency. You recommend what? Burn less coal. Make less electricity. Decrease the irreversibilities in the pump. Increase the reversibilities in the compressor. Or increase work output of the turbine. You can talk to your nearest neighbor, but don't stand up. Let's see how we did. Get the turbine to produce more work and you'll be fine. You're hired as a new engineer at a new electric generating plant. Your new boss says the plant uses the most efficient cycle, the ideal Rankine vapor power cycle. Your boss says you need to make sure it remains the most efficient plant in the world. You are asked to find ways to improve its thermal efficiency. You decide to do an exergetic analysis of each component. Where do you begin your analysis? What component has the greatest exergy destruction in that plant? All right, I got to stop it. And what component has the greatest exergy destruction in the plant? It really is discussed in the textbook. And it's not all that intuitive. But there's a whole lot of exergy destruction when you have heat transfer. And the greatest source of exergy destruction is in the boiler. It's in the boiler. It's in the book. How many people remember reading it? 1, 2. All right. Oh, well, terrible. What fossil fuel is typically used in an electric generating power plant that uses a Rankine vapor power cycle, what fossil fuel is typically used? Coal, natural gas, nuclear, wind, or photovoltaic? From hard to easy, I know, but hey, I'm trying to get on your good side again. And one of the words that some people will miss is this word fossil. I don't understand what fossil means. Oh, come on, I didn't explain it, but it's out there in the literature and everything else. Is wind and fossil fuel? No. Photovoltaic? No. Nuclear? No. No. Okay, so our choices are down to coal and natural gas. If I had natural gas, I would put it through a gas power cycle, a Brayton cycle. The coal is a fossil fuel, and you cannot put coal. Yeah, you can pulverize coal, turn it into synthetic gas, and make it act like natural gas, and then do it. But CPS committed to invest in an exploratory power plant like that, and then pulled out when the price of natural gas plummeted. They canceled. They didn't renew their option to stay in that plant. But anyway, the best answer is did I ask the right question? Isn't it A? Last one. Your boss. Hey, you have a lot of bosses now. Your boss thinks it would be good to convert the current plant into one using a supercritical vapor power cycle. There's a new word, supercritical. You say the plant will need to be changed so that what? A is true, B, C, D, or E? It's going to be now a supercritical vapor power cycle. I wish I knew what a supercritical. So what's the deal with the supercritical? Well, you think about a temperature entropy diagram. You put a dome. What is that point right there? What's that point? The critical point. You got to be super above. If I said draw a line of constant pressure, you draw something like this. I said draw a line of constant pressure where the pressure is greater than the critical pressure. Can't exist. No, it can exist. The line does something like this, doesn't it? And you can actually operate power plants at pressures above the supercritical, above the critical pressure of water, of steam. And so that just means you don't have a distinct phase change. What's the quality of this out here? There isn't any. It doesn't go from saturated liquid to saturated vapor. It just sort of changes from a heavier, denser substance to a substance that has a larger specific volume. And if you looked at it, you could probably find YouTube videos that show you a picture of what does it visibly look like. What does a supercritical fluid look like? And it's kind of like a cloud, dense fog or cloud. Okay, so which of these are the best option? The quality of steam entering the turbine is greater. No, you can't have it greater than 100%. It's not defined. Where do you define quality? Only in the dome. Only in the dome. At the edges of the dome, yes, but not outside the dome. The quality of steam leaving the turbine is greater than, no, again, steam pressure entering the turbine is greater than the critical pressure. Steam pressure entering the turbine greater than the critical pressure. Looks okay, but let's keep looking. The steam pressure leaving the turbine is greater than, it leaves the turbine at low pressure. And then none of the above. Well, I got a contender. Isn't that my contender? I think we'll go with, hey, that's pretty good for your last clicker question for today. Oh, I never closed it. Oh, I got to close it. Now I'm going to grade it. Now I will grade. I didn't even look to see if there were people piling up on C or not. Well, with that, I'm going to pause, stop, and give you a lecture. I'm not a lecture. I'm going to give you a quiz. Thank you for your attention.